Hey guys, welcome to another video in the video lecture series on digital signal processing. In this video, the topics we are going to cover are as follows. So let's get started. DSP can be programmed to perform a variety of operations such as filtering, spectrum estimation, etc. Depending on the application, a DSP may be realized using a computer or a special purpose chip or a field programmable DSP. There are two key concepts to any DSP application. They are sampling and quantization. We will see more about these as the video progresses. Any DSP application involves three stages. Stage 1. Conversion of the signal from analog domain to digital domain using sampling and quantization. This process is called analog to digital conversion. Then the digital samples are processed using a digital signal processor, and the resulting output may be converted back to analog form if required using a digital to analog converter. Now let's see a review of analog signals. The frequency spectrum of a signal x of t can be found using the Fourier transform formula, which is this. The ordinary frequency is related to omega as omega is equal to 2 pi f. Inverse Fourier transform allows us to express a signal as a sum of complex sinusoids. This is the formula for inverse Fourier transform. Laplace transform is a transform which can be applied on any continuous signal x of t. Laplace transform x of s is given here. The Laplace transform becomes the Fourier transform of a signal when s is equal to j omega, which you can see here. The output of a linear time invariant system given an input x of t, where h of t is the impulse response of the system, is given as this. The output is a convolution between the impulse response and the input. In frequency domain, convolution becomes multiplication. So y of omega can be expressed as a product of h of omega and x of omega, where h of omega is the frequency response of the impulse h of t. We know that sinusoids are eigenfunctions of LTI systems. So given a sinusoidal input to a LTI system, we get a scaled version of the same signal as the output. This property can be exploited to use LTI system as a filter, and let's see how. So let's take a signal x of t, which is sum of two complex sinusoids, and y of t being the output of the LTI system gives out a scaled version of the input. So as we have already seen, y of omega would be a product of x of omega and h of omega. We can design our system such that h of omega 1 would be 1 and h of omega 2 would be 0, resulting in this spectrum being eliminated. Now let's move on and get started with the sampling theorem. Sampling is a process in which a given analog signal x of t is measured periodically every t seconds. This process represents a very drastic operation of chopping, and thus introduces a lot of spurious high frequency components into the frequency spectrum of the sampled signal. So there are two issues one has to take care when sampling. They are, what is the effect of sampling on the original frequency spectrum, and how should one choose the sampling interval t? Let's discuss. So what we observe is that these new high frequencies f plus fs, f plus 2fs, etc. are periodic with a period of fs, where fs is 1 by t and it is called as the sampling rate. It's the inverse of the time period between the samples. Here we can see the effect of sampling on a signal x of t. Let's try to understand the replication of frequencies using a sinusoid. X of t is equal to e power 2 pi j f into t, where f is the frequency of the sinusoid. Its sampled version, x of n capital T, can be represented as the product of an impulse train, where the impulses are separated by a time period capital T and the original signal x. So, as x of nt can be represented as product of these two, the frequency spectrum of x of nt, capital X1 of omega, would be the convolution of the frequency spectrum of x of t and delta of t minus nt, which would be frequency spectrum of x of t being repeated in every 1 by t frequency difference, thus giving us a graph something like this. There is also another issue with replication of spectrum, which is one cannot uniquely find the original frequency of a signal looking at the replicated spectrum. The potential confusion which arises because of this is called as aliasing, and sampling theorem provides us a way to avoid it. Let's see what is sampling theorem. The sampling theorem provides a quantitative answer on how to sample a signal so that its variations are not lost, and it also helps us in preventing aliasing. There are two criteria to be met if one wants to accurately represent a signal by its sampled version x of nt, and they are: the signal x of t must be band limited, with say a max frequency being f max, that is, after f max the frequency spectrum x of f should be 0. And the second criteria is that the sampling rate fs must be chosen to be at least twice that of the maximum frequency in the frequency spectrum, that is, fs should be greater than or equal to 2 times max of the frequency present in the frequency spectrum. The value fs by 2 is called as folding frequency, and the interval minus fs by 2 to fs by 2 is called as Nyquist frequency interval. Fs by 2 is also the cutoff of low pass analog pre and post filters, which we will see later on. Now let's discuss about anti-aliasing pre-filter, and let's see why do they come into the picture. Practical signals are not band limited, so they don't meet the criterion of sampling theorem. In order to sample those signals, we pass them through an analog low pass cutoff filter before sampling. So this helps make the signal band limited. The cutoff of these low pass filters is taken to be fs by 2, and one has to be careful in choosing fs so that they don't lose any significant spectrum components. Like here, we are losing only minor portions of the spectrum, and that is the reason they are called as anti-aliasing pre-filters, because they help meet the criterion of sampling theorem and thus help in avoiding aliasing. The cutoff of these filters is said to be fs by 2. Hardware restrictions prevent us from choosing any fs we desire. Just like sampling theorem provides us with a lower bound on fs, which is twice that of the maximum frequency present in the signal, the hardware limitations provide an upper bound. So let's see how. After input signal is sampled, the samples are quantized and then processed by DSP. And this takes some time. So if the time taken to process one signal is say t-proc, we should send in the next signal only after this has been completely processed. That is, the time period difference between sampling of two signals should be at least greater than or equal to t-proc, which in frequency terms converts to fs being less than or equal to fproc. So the overall condition on sampling rate is 2f max less than or equal to fs less than or equal to fproc. Now let's discuss sampling of sinusoids. The two conditions for sampling theorem, the band limitedness and the minimum rate for choosing fs, can be shown using sinusoid signals. Consider a signal x of t is equal to cos 2 pi ft. The signal is sampled at different fs, 8f, 4f and 2f as shown here. If we observe the picture, we see that the minimum sampling rate should be 2f, so that we correctly cover the variations of the signal, and from which we can show that intuitively fs by f should be greater than or equal to 2. And if our signal is a sum of some complex sinusoids, then we would have to choose fs such that it is greater than twice of the max frequency in the given signal x of t. Now let's see about analog reconstruction and aliasing. Consider a complex sinusoid signal x of t is equal to e power j omega t, where omega is 2 pi f. Its sample version looks like this. Now consider a family of sinusoids xm of t such that xm of t is equal to e power 2 pi j into f plus m times fst. So on careful observation, we find that the sample version of the new family of sinusoids matches with that of x of t, that is xm of nt is equal to x of nt. The sample signal is same for both, even when the original signal is different. These signals are aliased, so the sampled values cannot uniquely determine the original signal from which they originated. So what happens when we pass this version through an ideal reconstructor? What it does is it extracts all the components in the Nyquist interval, that is from minus fs by 2 to fs by 2, and zeroes out the ones which are outside this interval. Among the set of replicated frequencies f plus or equal to mfs, there is a unique value which lies in the Nyquist interval, and this is given by fa is equal to f times mod fs. We can observe that fa is equal to f when f lies in the Nyquist interval, that is mod f is less than fs by 2. This shows that fs should be greater than 2 times f, which is a criteria in the sampling theorem. The second case is if mod f is greater than fs by 2, the output of the reconstructor would be xa of t, which is e power 2 pi j fa into t, where fa is f mod s and is not equal to f, results in aliasing. So this gives us a clearer understanding of sampling theorem. Let's take an example to get a better understanding. Consider x of t is equal to this, and let this signal be sampled at fs is equal to 2 Hz. On reconstructing using ideal reconstructor, we get the output to be xa of t is equal to this, which is different from the original signal. This has happened because f1 is 1 and f2 is 3 Hz. If we would have sampled at greater than or equal to 6 Hz, aliasing would not have happened, but we have sampled at 2 Hz. because of which the second part got aliased and we got a different output than the original signal. One way to overcome this problem is using oversampling. This oversampling method also helps us tackle the imperfections of ideal pre-filters in a reconstructor. A more intuitive way to understand sampling is by using a rotational motion, where we consider a complex sinusoid being represented as a wheel moving with f revolutions per second speed. The wheel is set up in a dark room and can be seen with the help of a flashlight, which is flashing at fs flashes per second. The rotational frequency omega is given by 2 pi f, and the angle the wheel turns in t seconds is given by capital omega, which is omega times capital T, which is this. Here W is called as the digital frequency. The quantity f by fs, which is equal to f times capital T, is also called as digital frequency. This gives a measure of the number of revolutions made in t seconds by the wheel. So ft represents the number of revolutions made by a wheel in t seconds. But if the wheel is moving with a higher frequency, say f plus m times fs, then it would complete ft plus m revolutions. But an observer would miss this, as the speed perceived by him would be f of mod fs. Let's see with the help of an example. In case 1, we have two wheels, one making 1 revolution per second and the other making 5 revolutions per second. We are observing this with the help of a flashlight, which is being flashed at t is equal to 1 by 4 seconds. So we would first observe wheel 1 to be here. At the next time when the light was flashed, we would observe it to be here, then here, and so on. Thus, the speed perceived by the observer would be 1 revolution per second, which is same as the one the wheel is moving in. But in case 2, this is the position in which we observe the wheel the first instant, and then it has moved 5 by 4 revolutions, which means it comes back here at the second instant, and then here at the third instant, and then here, and so on. We would perceive this to be moving in the same speed as that of the wheel 1. So here we see that the frequency perceived by the observer is f mod fs, here f being 5 and fs being 4. The relative speed seen by the observer would be 1 revolution per second, but which is not true. So this sheds some light on choosing proper fs. And in this case, f is equal to 9. It's covering 2 revolutions which are being missed by the observer. Here, when f is minus 3, minus indicates the opposite direction. We perceive it to be actually moving in the same way as wheel 1. Here, not only the speed but the direction is misconceived. So it's important to choose fs properly so that we don't miss extra revolutions being made by the wheel. This can be analogously compared to that of signals. Moving on. A sample sinusoid can take form in one of the following units: t, which is also equal to 1 by fs, and then 2 pi f, which is equal to omega, and we have already seen before that omega t is capital omega. Also, there are various frequency scales commonly used in DSP. These interval is the Nyquist interval, and in one form of the sinusoid, the frequency scale is this in the others. Now let's move on to spectra of the sampled signals. Let's start with practical sampling. The output of a sampler can be considered to be an analog signal consisting of linear superposition of impulses occurring at the sampling times, with each impulse weighted by the corresponding sample value. So this here is a more formal definition of sampling. In practical cases, each sample must be held constant for a short period of time, say tau seconds, in order for the analog to digital converter to accurately convert the sample to digital format. That is, it's not just an impulse, it's a flat signal for tau seconds. This image would shed more light into this. So, but for simpler calculations and other stuff, we generally consider it to be an impulse. Discrete time Fourier transform. The spectrum of a sampled signal is its Fourier transform. We can derive discrete time Fourier transform formula from this, and let's see how. So we replace the sample signal x of t with this as we have discussed in the previous slide, and then interchanging the summation and integration, it takes this form, and on integrating this we get this output, that is, this is only valid at t being the multiples of capital T. So this equation is called as the equation of dTft. The samples x n of capital T can be recovered by inverse Fourier series, and the formula to do that is this. So this is the dTft which we have found of a given sample signal, and this is the Fourier transform. These are interrelated. Let's see the relation between the frequency spectrum of a signal and its sampled version. This is the Fourier transform of a signal x of t, and it can be appropriated to that of x of nt when t tends to 0. So here when t tends to 0, the summation becomes limit, because nt becomes a continuous variable then, and this equation takes the form as that of Fourier transform. But practically, to make computation, say in computer, we can take only finite sample, leading us to this approximation, where n is not from minus infinite to infinite, but is over a finite range. Just like we have Laplace transform in continuous signals, analogous to that we have Z transform, and Z transform is defined using this formula. Moving on to spectrum replication. We can actually show the property of spectrum replication by deriving the precise relationship between spectrum of sample signal and the original spectrum of the analog signal. So this is the sample signal we have, and the impulse chain is being represented by S of t. Now we have found the Fourier transform for S of t, which is here, and then we have expressed S of t as a sum of sinusoids. The Fourier transform of impulse chain is 1 by t, and this is the inverse Fourier transform, which is used to express S of t as a sum of sinusoids. Substituting it back here, we get the sampled version of the signal to be in this form, and when you find the Fourier transform of this, we get x cap of f is equal to this, and here we see that the frequency spectrum xf is being repeated at a period of fs continuously. This picture here sums up what we have discussed in the last slide. So the distance between two samples here, delta, is equal to fs minus 2f max, and it is also called as the guard band. If delta is greater than 0, it implies that fs is greater than or equal to twice the maximum frequency, thus satisfying sampling theorem, and so we don't observe any aliasing. But if delta is less than 0, then replicas intersect, leading to aliasing. This result here, the approximation or the relationship between x of f and the version frequency spectrum, holds in the Nyquist interval when delta is greater than 0. The figure here compares the spectrum we would like to compute, which is represented by the dotted line, versus what we can best compute and what the computer would actually compute. That is, we are comparing the three cases where this is x of f, this is the practically limited range one where L is a finite number case. If you might remember, we had discussed that a few slides ago. And what we could compute the best, that is when L tends to infinite. Practical anti-aliasing pre-filters. So an ideal anti-aliasing pre-filter removes all the frequencies outside Nyquist interval, which we have seen previously. Whereas in practice, anti-aliasing pre-filters look something like this. This is an ideal pre-filter. A practical pre-filter is almost flat in the passband region and then keeps attenuating till it reaches the stop band. After stop band, it becomes zero. So when we pass a signal to an ideal pre-filter, it would extract all the signals in this range and leave out the ones which are outside this range. Whereas a passband signal would take the frequencies in the passband almost correctly, while this part is attenuated a bit. And the attenuation here can be calculated using this formula. The point or the frequency f stop can be calculated using fs minus f pass. Fs by 2 here is in the middle of f pass and f stop. So what we try to achieve here is that the pre-filter must be essentially flat over passband in order not to distort the frequencies of interest. Even if it is not completely flat, it can be equalized digitally at subsequent processing stage by digital filter. So what we do is we try to do the inverse of what a practical anti-aliasing pre-filter would do. So say a part gets multiplied by 2 here and a part doesn't get multiplied by 2 here. So this becomes twice the frequency which we would want, but this is the correct frequency. So on multiplying this with half and this with 1 again, so 1 by 1 is 1, we would get back the exact frequency spectrum we are looking for. And attenuations are additive in nature. So that's about practical anti-aliasing pre-filters. Let's move on to analog reconstructors. Let's basically see what reconstructors are. Reconstructors fill the gap between samples, either by holding the value constant till the next sample or by putting a curve in between the two samples. Filling gaps results in a smoother signal than the sampled signal, which in frequency domain translates to the higher frequencies in the samples being removed. Thus, any reconstructor may be viewed as an analog low-pass filter. Let's see the relationship between the reconstructed output to the input samples, and which is given here. So these are the samples. So passing through a analog reconstructor, it's being convolved here, and the output y of a can be represented in this form. which translates into frequency domain like this, because convolving in time domain is also equal to multiplication in frequency domain. So we obtain the relationship between the reconstructed output to that of the input samples here in this form. So let's see ideal reconstructors. Ideal or perfect reconstruction can be done when Ya of f is identical to the original analog spectrum Y of f. The ideal reconstruction filter HF, this is the frequency response of an ideal reconstruction filter. So its ideal low pass filter with cutoff being Fs by 2, which is the folding frequency, or this interval being the Nyquist frequency interval. So the value of T for passband gain for an ideal reconstructor is justified because we have seen for a perfect or ideal reconstruction, Ya of f should be identical to Y of f, and Ya of f, which we have obtained from this derivation, is this, and Y dash of f, which we have seen previously, is equal to 1 by T times Y of f when we see only in the Nyquist interval, and an ideal reconstructor removes all the spectrum outside the Nyquist interval. So Y cap of f would become 1 by T times Y of f. So it makes sense in H of f being capital T. Thus Ya of f would become Y of f. The impulse response of an ideal reconstructor can be found using the Fourier transform. So on simplification gives us this. In general, ideal reconstructors are not realizable because impulse response of an ideal reconstructor is not causal. Therefore, we use alternate reconstructors such as the staircase 1. So this is the H of T for the ideal reconstructor. Let's see the staircase reconstructors. The staircase reconstructor is the simplest and most widely used reconstructor. Its impulse response H of T is given by this equation. It is 1 for a time period capital T, that is between two samples. So H of f, that is the frequency response of this, can be found using Laplace transform. So first we find the Laplace transform of H of T, and then on substituting S is equal to this, we arrive at this point where this is the frequency response of the staircase reconstructor. We see this is a collection of curves which tend to become 0 at multiples of Fs. This is an ideal reconstructor which we have already seen. This is the frequency response of an ideal reconstructor. It extracts all the values in the Nyquist interval and lays out the remaining, whereas this curvy thing is the impulse response of staircase reconstructor. So on passing a signal to a staircase reconstructor, we would be left with partially attenuated central replica, because this is not a flat band but a curve, and a few surviving replicas. So in order to remove the surviving replicas, we use something called as anti-image post filters. These are additional low pass filters which are put at the end of reconstruction to get a better result. In time domain, the post filter has the effect of rounding off the corners of staircase output, making it smoother. The main function of post filter is to remove the remnants or spectral image survived by the staircase DA reconstructor. So this here is the frequency response of a anti-image low pass filter. We can see this has a sharp cutoff, unlike the staircase reconstructor, which is more smoother. Thus, if you see, these extra spectral images which were left have now been removed. Now let's see the basic components of a DSP system. Minimum DSP system or minimal DSP system would consist of at least these things, which include a low-pass analog anti-aliasing pre-filter to band limit the signal to be in Nyquist interval, an analog to digital converter to sample and quantize the analog signal to convert it to digital domain. Then of course you have a DSP, which could be a dedicated chip or a computer which is mimicking the function of a DSP. And then you could have a DA converter, which would help you convert back the digital signal to analog domain. And then we have a low-pass anti-image post filter with a staircase reconstructor or an ideal reconstructor. So first we reconstruct the digital signal, the digital samples, and then remove the extra spectral images to get the input which we have given. This slide here sums up what we have discussed in this video. This diagram represents the overall process involved in taking an analog signal, doing digital signal processing on it, and giving out the output again. So these represent the various stages. So guys, thank you for watching the video. For more reference, please refer Introduction to Signal Processing by Orphanets, and I'm also going to put the slides link in the description below.